Okay, so let's continue, shall we? So we just finished chapter 2, and so what we've done, if you remember, is we've done a bit of an algebra review, and then we've looked at the idea of a derivative, and the main thing we've been doing is just thinking of derivative, thinking of rate of change. So you know how to calculate a rate of change. If it's given to you graphically, you take a slope. If it's a formula or a table, you look for a little interval with the point that you're interested in taking the rate of change of in the middle, and you do rise over run. Okay, so the rate of change, you can think of that as like kind of like the velocity, how fast something's changing. You can think of it as a slope of a graph. You can think of it, you've got this marginal interpretation. So when we say the derivative is 5, well, we think about 5, the units. It's like 5 people per day. So the marginal interpretation is that if we had an extra day, we would have 5 extra people. That's that marginal interpretation, which is a good way of thinking about derivative. Extending the marginal interpretation, we can think of the derivative as a multiplier. So it multiplies, you multiply it by change in x to get change in y. So if the multiplier is 5, then we multiply 5 by whatever the change is. So if we have 3 extra days, that's 15 extra people. If we only have half a day, that's 2.5 extra people. Okay, so hopefully now you've got like a good sense of what a derivative is. And so for this chapter, in chapter 3, we're going to concentrate more on formulas and kind of just figuring out some rules for actually calculating the derivative. Okay, so yeah, so that's our plan for the next little bit. Okay, some formulas. So we already know some just by common sense. Okay, so for example, if our function is a constant, so if the constant never changes, what is the rate of change? 0, yeah. That's just common sense, that one. Another one we know is, say, our function is a straight line. That's another one where we know we can say what the derivative is straight away. Which constant is it? In this case here. M, yeah. Since the derivative is the slope, if we have a straight line, we know what the slope is. We usually denote that by m, so we can do that sort of straight away. Okay. What about we have our function and we multiply it by a constant. What is the derivative of that in terms of the derivative of our original function? So let's have a think about this. Well, how do we figure out derivatives? We do rise over run, right? So we'd think that, you know, f of x derivative, how do we get to it? Well, we look at maybe f of x1 minus f of x0 over x1 minus x0. Right, we take a tiny little interval, and as it gets tinier and tinier, we see that we get the derivative. Well, what happens if we replace our constant, our function by a constant times the function. Now here's when we have to do some algebra. There's not much algebra we can do here. What algebra can we do here? So here is c times that, here is c times that. What's the common factor? C. So we can write this as c times fx1 minus fx0 over x1 minus x0. Okay? This is f prime of x. Right, this is how we would figure out the derivative of f. So all we've got here now is c times the derivative of x. And so that's another rule we can get, that the derivative of a constant times a function is a constant times. Like if we're making everything 5 times bigger, then the change is going to be 5 times as much. Okay, so this is our first rule where we've actually had to do some thinking to get it. Now, what we're trying to do now is just figure out some rules of derivatives. Like if I give you a formula, we want to get to the stage where you have a formula for the function, I can have a formula for the derivative. So the rules come in 2 flavors. Okay? The first type of rule is you're given a specific type of function. It could be an exponential, it could be a logarithmic, it could be a power function, it could be a trig function. We need rules for being able to figure out the rates of change of those. Okay, so that's one kind of rule. The other kind of rule is we look at kind of like the arithmetic of functions, like how do we make functions? The usual way we make functions is we have this toolkit of simple functions like, you know, linear, exponential, whatever, and then we stick them together in various ways. We can add them, we can multiply them, we can divide them, we can take roots of them, we can compose them. There's all sorts of different ways that you can make functions out, complicated functions out of simple functions. And so the second type of rule is, well, how does that change the derivative? So this is an example of that second kind of rule. Okay, so if we know the derivative of a function, we know the derivative of a constant multiple of that function, because that's one way we can make new functions from old functions, is we could just multiply them by a constant. Another simple way is what happens if we add functions together. That's an easy way to create new functions. Okay, so for example, we could have one function being cos x plus e to the x, or you know, log x plus x squared. So what we want now is a rule, like if we know the derivatives of the individual pieces, how do we get the derivative of their sum? Okay, so let's go about. We're going to do the same kind of trick that we did with the constant multiple. Okay, so the derivative is going to be approximately what? We're going to look at f of x1 plus g of x1 minus f of x naught plus g of x naught x1 minus x. So that's how we would go about actually figuring out its derivative. Okay, we've got to do some algebra now. What's the only bit of algebra we can really do? There's really only one thing I can see to do. What's that? Remove the brackets?
Yeah.
I mean, that's the only thing I can see. So let's go ahead and do that. So that's f of x1 plus g of x1 minus f of x naught minus g of x naught. Okay. Be careful. This is one of the most common mistakes that I see is when people remove brackets and there's a minus sign involved. You've got to be really careful in distributing that minus sign. Okay. Again, there's not much we can do algebra-wise, but a good thing is always put like things together. That's kind of like a basic thing we do in algebra. So that's going to be f of x1 minus f of x naught plus g of x1 minus g of x naught over x1 minus x naught. And so now I'm just going to separate them out into f's and g's. So this is f of x1 minus f of x naught over x1 minus x naught plus g of x1 minus g of x naught what's this?
The derivative of x.
It's the derivative of f, and this is the derivative of g. So this is that's a really simple rule, right? The derivative of a sum is the sum of the derivatives. It's even like a little poem. Even. Now, this would have been the same if I had put a minus sign here, right? If this had been a minus, we would have ended up with a minus there. So the difference, the derivative of a difference is the difference of the derivatives. These rules are pretty simple, right? I have to warn you that this is not true for products or division. We get a much more complicated answer, but we'll see that. We'll get to that later on. Okay, so these are these two are examples of what I call the second type of rule, where how we take derivatives of combinations. So we've actually got to start doing some derivatives, some actual functions. So the easiest the easiest ones were the why did I do that? Okay. What I recommend you doing is somewhere on a piece of paper, keep a list of the derivative rules and use it for when you're, doing your homework, so that you can learn that. Power. Next, we're going to look at the power rule. And so by the power rule, what I mean is, what is the derivative of a power function? So we've seen, so we know that the derivative of x to the 0, right? X to the 0 is just 1. The derivative is 0. The derivative of mx, or the derivative of just x, is 1. Okay, we've seen that the derivative of x squared is something linear, right? Because when we have something which looks like that, the derivative looks something like this. It looks something linear. So it looks like for a power, when you take the derivative, it becomes like a lesser power. And that's actually true. So let me actually give you the rule. The actual rule is n times x to the n minus 1. It's a really nice, simple kind of rule. So down comes the power, and we subtract 1 from the power. Unfortunately, it's a little too simple, so that people are tempted to say, oh, the derivative of e to the x. Oh, shouldn't we bring down the power? And no, the exponential is a different function, right? Because the x is in the exponent, not in the base. This power rule only works for power functions, only for functions where the variable is in the base. Okay, now why is that so? Well, let's do the same thing kind of like we do over here. So what would the derivative of x to the n be? Well, we'd like to do it as a rise over run. So maybe we'd have x1 to the n minus x0 to the n over x1 minus x0. Right, that's just doing rise over run. Now we've got to do some algebra. What kind of algebra do we want to do? I mean, there's not much we can do here. But what's our dream of being able to do? You've got
just cross the walls. Just like cancel now.
Cancel, right? Yeah, we want to factor and cancel. That's the thing that we like to do with polynomials, right? We like to see if there's a common factor, and we see there is a common factor, right? Because if x1 equals x0, this is 0 and that's 0. So this is a factor of that, and here is the answer. This is just an old algebra, so it's not completely obvious, but you can see it because if you multiply this out, you actually get this, right? Because if we multiply x1 by this, we get x1 to the n, and then we get x1 to the n minus 1 times x naught, blah, 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 all these sort of things. But then when we subtract x naught, right, we get a minus x naught times x1 to the n minus 1. That cancelled the x1 times x1. So that times that cancels that times that. It's what we call a telescoping sum. So we do, whenever we put a plus, we're also putting a minus later on. And so the whole middle just collapses like a telescope if you actually multiply this out. And the only thing left is the first one times this, and the last one times that last one, which is x1 to the n minus x0 to the n. So that's just a nice algebra trick. I'm not expecting you to repeat that, but that's showing. But your dreams come true. We've got cancellation. Okay? And so now we're left with all these things here. But what happens when x1 is really close to x0, so that they're basically the same thing? Right? We get this one is x1 to the n minus 1. Well, if x0 is basically the same thing as x1, that's x1. I'll just do approximately, like when they're really, really close. We get a whole bunch of x1 to the n minus 1s. How many of them do we get? We get n of them. So this is the reason why this rule works. It's just a nice algebra trick. And there's other ways. There's some other ways to do this if we formulate it in a different way. But in those ones, they're all the same. You multiply something out, you factor it, things cancel, you get that answer. So that's good. Okay, and so that, for example, if we've got x squared, derivative is 2x. There's that straight line that we've seen before. Remember when we did this kind of thing? And we went to see what the slope is. Well, it's increasing, goes from really big to really little. So the derivative was something like that. Well, this is a cubic. The derivative of a cubic is 3x squared. So again, we see it. So that's kind of matching up with the examples that we've seen before. So that's all great. So the nice thing about this rule is when I proved it, I only proved it really for positive integers. But actually, it's true for all powers. They could be fractional, they could be negative. We get the same kind of result. And the algebra is harder, so we won't go into it, but trust me, it works. So, for example, let's say we want to do the derivative of 1 over x cubed. Well, as a power, what's 1 over x cubed? What's the power of x in there? What happens when we do fractions? Yeah. So that's the same thing as the derivative of x to the minus 3. So now we can use the power rule. So down comes the power, minus 3, and we subtract 1 from the power. We get x to the minus 4. Which of course is minus 3 over x. Derivative of square root of x. again, we can write the square root of x as a power. That's x to the 1/2. Okay. Down comes the power, and we subtract 1 from the power. And that's the same thing as that. Although if you're doing a homework answer, this is good enough. But it's true for anything. So for example, if we replace a 3.5, it's down comes the 3.5, and we subtract 1 from the power. So power rule is always a favorite among students just because it's easy. So if you've got a problem with that, you know what to do. Yeah. So, but now, since we know the power rule, and since we know the addition rule, we can now do any polynomial. So, for example, if we had x cubed plus cubed root of x plus 12 x squared. Let's put numbers in front of these.
Sorry to interrupt you, Alex.
Did you leave something?
Did you leave my keys in?
I don't see anything. No.
Oh, that's something. Thank
Okay.
you. Sorry to interrupt you.
It's no problem. Okay, so in previous classes you would have recoiled in horror at this because it just looks so complicated, but it's really easy, right? Because all you've got to do is a sum, so all you have to do is each individual one, and each one's a power, and you know how to treat this. So it's 7 times the derivative of x cubed, which is 3x squared, minus the derivative of x to the 1/3, which is 1/3 x to the minus 2/3, plus 12 times the derivative of x squared, which is 2x. So you just break it up into its part, and you take the derivative of each part. And so the last step would be just kind of like a tidying up. 21x squared minus x to the minus 2/3 on 3 plus 24x. That would be your answer. So that's a nice thing about rules. Like if once you know them and you know how a function is put together, you just apply the rules, you break it up into simple pieces, you take the derivative of the simple pieces, and then you put it back all together. So it all turns out fairly straightforward. Okay, so what kind of questions can I ask you? So I could ask, I'm just going to try something. Okay. So what kind of questions have I been asking? So, so one question you can see straight away is if I give you a formula and I ask what is the derivative of that equation, of that function, you've now got to know how to do this. But there are other ways that I could ask questions. So we know that derivatives is the slope of the tangent line. So a question I can ask is, what is the tangent line of some function at some point, right? If you think about it, well, let's have a function. So let's say 7x cubed plus 3x plus 2 at, say, the point x equals 1. Okay. So what information do I need to give you for you to give me a formula for the tangent line? It's a straight line, so what kind of information do you need? A slope and a point, right? Well, the point is easy, right? Because we've got the function. So f of 1 equals 12, right? 7 plus 3 plus 2 is 12. So it goes through the point 1, 12. What's the slope? Well, we need the derivative for that. It's equal to 21x squared plus 3. Right? Down comes the 3, subtract 1 from the power. The slope of 3x is 3. So f prime of 1 is 24. So we know that the slope is 24. So with those bits of information, you can write down the slope of the straight line, right? It's going to be y minus 12 equals 24x minus 1. Is everyone comfortable with that? Going from that to that? That's just using the point slope formula.
How did you get 24 again?
24, I plugged in 1, or 21 times 1
Oh, okay.
plus 3 is 24.
Okay.
And then the last thing I would do is just tidy it up. 24x minus 24 minus 12 is plus 4. There's the tangent line in the point slope form. Okay. Now that I've got,
So the 2 goes away because it's just times x to the 0, so it just like,
right, because what happens when I add a constant to a function? It just moves it up or down, right? Does it affect the slope? No. Right. Because we know the derivative of just a constant by itself is 0. Okay. So it doesn't affect the thing. Now that we've got a tangent line, we can answer other kinds of questions. Like the question could be, use tangent line to approximate 1.1.
why would it be 12? Would it be different?
That's the y-intercept of the tangent line.
Oh,
Okay, so it's just whatever it is because it comes from this and from that. So don't expect this to be able to get that from this directly. Okay, it's not, because the tangent line, remember, only looks like the function near the point x equals 1. The intercept is when x equals 0, and that's far away from x equals 1. So it's not straightforward at all. Okay. These are kind of questions that I've been asking. So this is like saying delta x is 0.1. What is delta y? Well, if delta x is 0.1, and the derivative is 24, what is delta y? How did I get 2.4? Right, because that's thinking of the derivative as a multiplier. It multiplies change in x to give you change in y. Okay, so the approximation to 1.1 is 2.4 is the change in y. Well, what was the y to start with? It was 12. Right. Since I think that's what I want to say. Yeah. Did I do this right? Hey, sorry, this is minus 12. 24 times minus 1 is minus 24 plus 12. Now it works. Does people see what I did here? It's a little bit tricky. So what I did was this, using a tangent line to approximate 1.1, is basically asking, what is this function at 1.1? The answer was 14.4, and the picture looks like this, right? We've got our function, it looks like something. Here's our tangent line. And near the point where the tangent line touches the function, the tangent line is approximately the same as the function. So I've used this value here to approximate this value here.
So does that approximation have to change since it's minus 12 now, or is it?
No. The function actually is 12. So it affects, it's the base from this. Nothing to do with this. I mean, that was 12. So f of 1.1 is approximately f of 1 plus 0.1 times f prime of 1. And f of 1 is 12. Unfortunately, yeah, the fact that this is 12 has nothing to do with the fact that that's 12. Okay, you're looking suspicious, so let's do another one. Let's do a different one. Let's have another function. So let's have cube root of x at x equals 8. Okay, so again, we've got a point. So when x is 8, what is f? 2. So that's a point. We need the slope. F prime of x is 1/3 x to the minus 2/3, right? Because this is the same as x to the 1/3. Okay. What is f prime of 8? It's 1/3 8 to the minus 2/3. The cube root of 8 is 2. 2 to the minus 2 is 1/4. So this is 1/12. Okay, I've got a point and a slope. So therefore, I can do the tangent line. The tangent line is y minus 2 equals 1/12 x minus 8. Okay. I'm not going to do any further because I don't want to confuse you too much about the tangent line. So that's good because this is delta y, this is delta x. Okay. So let's use the tangent line to approximate the cube root of 8 and 8.5, for example. Okay, so we know delta y is 1/12 delta x. In this situation here, what is delta x? What's our base point? Our base point is 8. We want to do it at 8.5, so what's our delta x? 0.5, exactly. So if this is 0.5, 1/2, what's delta y going to be? What's 1/2 of 1/12? Yep. So expect the answer to change by 1/24. So if the old answer was 2, what is the new answer? 2 and 1/24. That's our approximation for the cube root of 8.5. That's pretty fancy. So yeah, we start. So this is why formulas are so useful. We can really kind of do a kind of whole lot of stuff about them. Other kinds of questions. So for example, I've got f of x equals x cubed. Its derivative is 3x squared. Its second derivative is 6x. What information does that tell us? Okay, what information do derivatives tell us? So what information does the first derivative give us? Increasing or decreasing, right? So the fact that the derivative is 3x squared tells us what? Is that positive? Is that positive or negative? It's going to be positive except at 0. So this tells us this function is basically always increasing. 6x, what information does that give us? That's the second derivative. What information does the second derivative give? Concavity, right? So it's concave down for x negative, and it's concave up for x positive. Okay, so that's always information you're going to be able to get from derivatives. You're always going to get information about increasing, decreasing, and concave up and concave down. So that's another source of questions I can ask you. I can give you a function. I can say, when is this increasing? When is it concave up? And you just take the derivatives and you just apply that there. I can give you a revenue curve now. I give you a formula. Let's say that revenue is 1,000 q minus 3q squared for some range. I don't know. the Q less than something. Basically, it can't go, it can't start going down. So however long that's valid for. So I can ask questions like, interpret R 100 and R prime of 100. Okay, so this is a revenue curve. So what is R 100? I mean, it's going to be a number. What does that number mean?
The revenue on 100.
Right. That number is going to be how much money we get from selling 100 items, 100 units. What's the R prime of 100 going to be? What is it in terms of economics? What's the derivative of revenue called?
If there's a negative on there, wouldn't that be the cost part too?
Sorry?
Like since there's a negative 3q squared.
Yeah, this is something to do with you flooding the market so that you have to sell it cheaper as you get more. That's why there should have been an upper bound here, because this isn't going to go forever, right? Because it is eventually going to go down. So I never want it to go down. So whatever you need here to make it, basically it's going to look like, I want it to look like this sort of thing. But what's R prime of 100? What does that mean? We can actually figure out what it is, right? We take the derivative, plug equals 100, but what information does it give us?
How much the 100
And what do we call that? There's a name in economics for the name of that extra unit.
the marginal utility,
No, not marginal utility,
marginal profit, revenue.
marginal revenue. Okay? So this is how much money we get from selling 100 items. This is how much money we get from selling the 100th item. So that's a useful thing. So the fact that we have a formula just means that I get more opportunities to ask questions like this. And I think that should probably do us for today. Yeah, that can do us for today. But hopefully that all kind of made sense.